Evening, everybody, and welcome to our talk on engineering art and guerrilla tactics. Thanks for Tim for the intro. So I'll talk about guerrilla tactics, what our interpretation of what they are. I'll do a very brief chat about who we are, a very brief chat about some of our recent work, and then I'll talk about the various, I suppose, what we call adversaries that will be tackled by guerrilla tactics. And what those tactics are. I mean, it's mainly revolving around projects and the techniques we've developed to deliver projects which are complex, fast, difficult to model, difficult to get your head around, difficult to communicate with people. So, I mean, that's the tone of it. So, guerrilla tactics. Now, I suppose there's a couple of definitions of guerrilla tactics. Wikipedia, which is the top quote, talks about it's avoiding head-on confrontations with enemy armies, instead engaging in limited skirmishes with the goal of exhausting adversaries and forcing them to withdraw. So we talk about what our adversaries are, but the RIBA, which is the bottom quote, has a slightly softer, I suppose, a more appropriate approach to this, which is talking about so winning by collaborating, leveling up skills, pooling knowledge, and how digital relationships can transcend local networks. So there's a bit of both in there. So I mean, I'll flesh this out in a second. Firstly, about us. Well, format engineers are a relatively new practice. We were formed in 2014. We think we're slightly unusual in that we're structural engineers, but the various people here have backgrounds in architecture, mathematics, geometry, coding. For example, we've got one guy who works part-time for the software house McNeil, who published Rhino, which a lot of you may know. We do lots of research. So we like to think we go beyond the narrow discipline of structural engineering. That's us. It's a very small team here in Bath, very beautiful team. I hope you'll agree, except for me on the right. We have our base here is in Bath in the west of England. We did have an office in London, which then got COVIDed, and it no longer is. But we also now have a small presence in Paris, which we are very excited about. We are winning our own projects there, which is good. I think that, we from the beginning were a very international company, and we're still 50% of our workload is international. And we're very keen to maintain that presence and that mindset, because we think that by exposing ourselves to more and different influences, not just being very insular, we're all the better for it. That's possibly a metaphor for life and politics as well. Now, so you will probably hear quite a lot about scripting and computation in this talk. As Tim said, we both sit on, I think it's the digital workflows and something panel. Tim, I'm not sure.
Thank you, Stephen. Yeah, thank you. And computational design panel, I've got it now. Digital workflows.
That's it, cool, yeah.
And computational design.
We should probably pay more attention to that. So we talk about scripting a lot. For those who don't know about that, it's establishing a mathematical, geometric, or mathematical relationship between different functions that enable us to produce, for example, the one basic way is a CAD drawing. Rather than the traditional 3D CAD drawing, you can define the elements in a 3D object via its symbolic relationship, which is great because it means we can change parameters very quickly and it regenerates that object. But we could also plug in things such as structural analysis to get results on the fly by changing elements of that structure. Or we can plug in things such as wind modeling, CFD modeling, all sorts of physical simulations. So it's a very powerful tool. But you'll also equally hear about first principle sketching and just, I suppose, disgorging the problems in your brain by the physical act of sketching. And that's something that we beat into people here. That's very, very important. It's not about jumping on the computer. I should also go back to the computer point and say, computing for us is it's not a philosophy, it's not a mindset, it's not an ideology, it's a tool. I lectured a bunch of architectural students yesterday, and I was ranting on about, computation design is not, it's not an ethos. It's a tool like a pencil, and it absolutely is. It just enables us to design better, leaner structures quicker and collaborate more easily. And there's also hopefully lots of talk of practicalities. You know, we pride ourselves on building things, and we pride ourselves on not just being the kind of engineers that say, oh, we do scheme and concept designs, you know. No, actually, we build the whole lot because we're very keen on what we learn from building is it fed back into the design process. So, I mean, practicality is something which shoots through all of our work. Just again, to set the scene, some of our recent work, before I sort of dive into the Guerrilla Tactics. Well, last year was quite an interesting year for us in terms of art. So we were very lucky to deliver quite a lot of projects in quite a short space of time. So, and we'll talk about these in more detail. Top left, Goodwood Festival of Speed. Top right, London Design Festival last year. Bottom left, the Tay Whale in Dundee, next to the Biennale in Dundee. Bottom right, Marble Arch Place. So those are all things that we were lucky to deliver last year. We're currently working on a number of quite interesting art projects. There will be, I mean, I'm sure many people on this call may have actually worked on similar structures, but we're working on a series of structures for a number of festivals, for a festival, a UK-wide festival this year, which was originally dubbed Festival of Brexit. I think it has a more palatable name now. But we're designing a number of enormous tree structures, which will be located in Birmingham and Edinburgh, which are there to reflect and illustrate biodiversity as well as urban diversity. So we're working with a really nice team of people on those projects. We've recently completed a very visual demonstration of climate change ahead of the COP26 conference, where we designed a sinking house. So this is it's a sleight of hand. This is anchored next to the historic Pulteney Bridge, or actually from the historic Pulteney Bridge in our hometown of Bath. So all the flotation calcs were us, all the calculations just proving this wouldn't float down the river and then crash into lots of boats, all by us. Timber lattice shell at Westonbirt Arboretum with architect Piers Taylor. We do our own footbridges. We're working on a number of contemporary bridges at the moment. Some, I think all of them are designed in-house, actually. Oh, there is one with an architect. I'll take that back. We not just work on art projects, we work on a number of, let's say, slightly more conventional projects, although they tend to have a sort of a twist to them or some sort of unusual aspect. We work on a number of contemporary houses that have long span cantilevers. We're working on a power station, for example, in the west of England. That's a huge project. Again, quite unusual shape. So we do tend to get involved in some quite interesting projects, which is something we're very, very proud of. We're working on a series of huge advertising structures in Qatar ahead of the World Cup this year. We do a lot of staircase designs, which is actually a lot more sexy than it sounds, in that we do lots of work for a steel fabricator doing staircases, which is great because we learn a lot about steel detailing. And we've learned a lot about dynamics. So it's from an outwardly quite, let's say, relatively straightforward set of work. There's some really, really interesting conclusions in terms of automating this process and understanding dynamics in quite some detail, which we apply to some of the works of art that we do. There's another staircase to illustrate the point. We've done some work with English National Ballet recently on their stage sets. We've done a lot of work at Foundation Lafayette in Paris on various works of art there. And we've done a number of things at the Orange headquarters in Paris. A lot of these actually led to our office in Paris. So Guerrilla Tactics. So just to recap. So we talked about exhausting adversaries and forcing them to withdraw. We talked about leveling up skills and pooling knowledge and collaboration. And then this is the RIBA sort of softer interpretation of this, and how digital relationships can transcend local networks. Well, so if in the context of this presentation, let's say adversaries are unusual materials, it could be the behavior of the material, or the structure is too complex to model. It could be how do we communicate? It could be it's too complicated to build, or quite often what happens is there's too little time to build it. That's a very common one in works of art. And some of the tactics we developed are developing our own tools, in-house tools, developing a particular mindset, a very can-do mindset, techniques which simplify the build, and a smart workflow and collaboration. Again, sort of setting up collaborative tools with artists. So maybe it's developing a script or a tool that we share with the artist that we can both communicate with to make everyone's life a lot easier. One of those I think I sort of home into techniques to simplify the build is something that we're really, really interested in. I do a whole sort of series of separate talks on that about social building, which is to say that it's very easy to design complex works of art, maybe with the knowledge that you have an extremely expensive KUKA multiple axis fabrication machine. But it's often harder and more fun, conversely, if you say, well, we'll limit ourselves to simple materials, or a simple CNC flatbed CNC cutter. What can we do with that? Can we then liberate the design process, or rather the construction process, for people who aren't experienced contractors to build their own things? Because they're quite complex things. I think I'm actually talking about that later on the year to the iStruct, but that's something that we're sort of super keen on. So each of these tactics, I'll try and separate them out, but there's quite a lot of crossover between the projects. So bear with me on that. So the first one, working with unusual materials. And as I say, what I'll do is I'll mostly use projects to illustrate this. Now, a lot of the work we do, well, some of the work we do stems from at least my colleague James's work at ITKE, where he was responsible for the Electra Pavilion. This is the Victorian Albert Museum, but it was also moved to Shanghai and the Vitra campus. So we've developed a pretty good knowledge of carbon fiber. This was a tower structure in Kentucky. We've also built from 3D printed sand. And we are currently building a pavilion, or a canopy rather, from 3D printed concrete. So these are novel materials. But how do you deal with these materials? They're often not codified. Well, I suppose one example of this, a quick example of this, was a project we did in Milan a couple of years ago. This is a 3D printed bioplastic pavilion. And there's some bizarre statistic, which is the world's largest recyclable bioplastic structure, which is a nonsense statistic. But each of the structures is made from a series of baskets. The baskets are flat 3D printed bioplastic, which is then linked together. So you can see it's all the flat elements here, making one whole. So how do you deal with this? Well, one way of dealing with this is, I suppose, the classic engineer's relatively low-tech testing approach, which is to say, okay, put in some strain gauges and we measure the materials and how they perform as a system. We'll load them, etc. We gain some data in that way, which is what we did on this project. So we're able to sort of look at the performance of the structure, where it was likely to buckle, and how we would reinforce it and deal with those elements. But I suppose the essential gist of this is that, by the use of computation, and apologies, this is very hard to actually read this particular diagram, but we were able to put every single member into our structure, and there must be millions of members in here. It's just a large data set. So by importing the geometry as a 3D model into the computational scripting, you're able to analyze and get the results, and then make decisions about the script, allow the script to automatically orientate the members in different directions, such as the red elements, which are the ones that were failing, there's far fewer failing, but just this is a simple flick of switches, orientate them a different direction, and therefore you get far less of them failing. And then we can automate the process and let the script sort of do its thing until they're all working. Or maybe we can look at removing elements automatically which are working hard, so loads of shed between elements which aren't working so hard. So by that method, by using huge data sets and with the sort of the knowledge you've gained from sort of pretty basic testing, we've been able to work with some pretty novel materials. And this is the final structure in its palazzo in Milan. As the top, the drone picture, the obligatory drone picture. So that's complex materials. Digging down to complex behavior. Now, some of these works of art, you often find that they're extremely complicated or don't obey the normal rules of beams, columns, etc. How do you mimic those? How do you simulate those with confidence? Now, one of the tools that we've developed in-house, at least, is we've developed, along with a researcher, Cecilia Brandt Olsen in Copenhagen, is a tool set which sits on top of the Kangaroo plugin for Grasshopper, which itself is a plugin for Rhino. And apologies if I'm talking sort of gibberish for some people, but essentially it's a way of simulating real-world physics in a digital environment. And our plugin, called K2E, essentially is a structural analysis plugin on top of that. So we can analyze very, very lightweight, very, very filigree structures using real-world physics, which means we can look at things like the bending active behavior of an element. What's the bending stress in there when it's pulled together? So very lightweight structures. And the first thing we ever tested this on was a structure at the University of West of England. Very simple timber pavilion. This is a number of years ago. I think this was the first structure ever to use that plugin. Series of bent active plywood strips. And how do you analyze the stress in those strips? Now, conventional engineering software struggles to do that, but ours doesn't. It instantly tell you what the pre-stress in those members are and what shape they will take up, most importantly. So that was an important test. So that's just one example. We developed a tool to actually mimic complex behavior. Another example is where we've developed our own CFD plugins. There are a number of CFD plugins out there in the world that enable you to check, visualize the effect of wind or a fluid upon a structure. But we developed our own on the back of the open foam, open source movement. Enables us to check some of the, I suppose, the more complex interactions between structural elements. And I'll come back to this actually at a later stage. So to illustrate, one example of complex behavior and the tools that we used to deliver it. In this instance, the same K2E plugin I've just mentioned. This is Goodwood Festival of Speed. Now, Goodwood Festival of Speed, for those who don't know it, is every year there is a festival. It revolves around cars, motorbikes, etc., anything fast. Near the south coast of England, they always have a big centerpiece structure. This is the first time that we've been invited to do it. And we were invited by Artists Unit 9, whose task was, or the task they were given, was the world's longest tensecretary cantilever. So when we first started talking to them, the debate was, what is the world's largest cantilever? What do we have to beat? Now, the one that we found, and there could be more out there, was this one by an artist called Kenneth Snelson. Now, Kenneth Snelson was a pupil of Buckminster Fuller. And he did a number of tensecretary structures. So we think this is in the States. And the kind of, I suppose, the joke is that we read the description on the internet wrongly. We thought this was 35 meters. So we were fixated by making our structure at least 36 meters. It was pretty firmly the world's longest. It turns out this is 25 meters. So we massively overshot. But hey, if you're going to do it, go for it. And the original artists So I suppose instruction to us was something like this: a tense-equity structure, which is a bit wibbly wobbly, a bit snake-like, undulates, has some randomness to it. We drew the scorpion on top to make fun, as you do. But then, so this was quite a nice collaboration with an artist, and they gave us a lot of freedom to determine the shape. So we said, okay, it needs to be a cantilever. How do you simulate a cantilever? So again, using computational design tools, we're able to build up this tense-equity structure from a series of modules. There it goes. We're able to relax it under its own self-weight, able to generate this structure, add a certain amount of randomness and wibbly wobbliness until the artist was satisfied that it was in line with their vision. And there was a whole series then of how do we make this, we lie this flat, and what kind of pre-stress is required to actually keep this thing in a sort of a stable configuration. What form does it need to be sort of preset to? So a lot of this work is all about simulating those forms. So this always gets lots of sniggers, apologies. So you allow this to generate form, and there you are. That's how you generate a tense-equity structure. So I suppose one of the beauties of this, we talked about with the adversaries, is not just complex behavior, it's lack of time. And here we were given a couple of months maximum to design the world's largest tense-equity structure and build it and get it fabricated and build it. And one of the ways we did that is to automate all the joint calculations. So they were all within the same scripting environment. So whatever we changed the parameters of the structure, the joints would automatically recalculate. We could see the stress in the joints, and we could play around with these different configurations and add stiffness. So it all happened within the same, let's say, parametric environment. And there are all the connections. All the fabrication drawings were done by us, and then were all, again, spat out of the same script to keep it super quick. That was the final structure, the 3D image of the final structure. It started fabrication. That was all fine. That was all good. And then it got to site, and the contractor we were working with is a Littlehampton Welding, who are brilliant steel contractor. They do some amazingly complicated things. And this, I think, was the first instance we've had a phone call at the weekend by the contractor to say, help, we've never failed to build a structure. Here, we might well fail because the clock is ticking and we're trying to build this 3D object in empty space. How on earth do you do that? So one of the things that we've heavily invested and researched is the use of augmented reality. And again, some of the tools fit within the computational design environment. There's a company called Fologram, an Australian company called Fologram, who do lots of work on this, who we've collaborated before. So we put the Fologram system on a series of iPads, a laptop, and we went to site. So we were able to see the structure, how it should be in relation to how it was. So then you're able to guide the contractor and say, well, that's not the right place. That should go over that one. That should go under that one, etc. And here you get a better sense of what that looks like. So the use of augmented reality here was absolutely crucial to getting this done on time. That was the final structure. Some of the detailing. That's the festival. So it was great fun. It was quite stressful. It was a very quick program without the tools that mimic the complex behavior, and the tools to allow us to spit out things like fabrication drawings and joint detailing super quickly. It couldn't have been done. How do we communicate? How do we talk with artists to get over this problem of, mean, my God, this is complicated. Tell me, what's the best way of proceeding from a blank piece of paper? So, I mean, one example is the Dundee whale I talked about before. This is working with an artist called Lee Simmons. Now, what Lee wanted to do is to stick to a very, very pure whale form. And what we wanted to do is put a structure in there, which is an actual two-way spanning structure. But it's very difficult to communicate in and sort of sketch options as to what the layout of that structure could be in 3D. So we used the work of a mathematician called Keenan Crane, who's at MIT, I think he's at MIT, to actually use his technique called boundary first flattening. There's one animation, this is probably a better one. Boundary first flattening, which enables somebody to draw on a 2D plane. So in here, we would draw a grid, cycling through grids of structure that the artist would find acceptable, which then get translated into an accurate 3D object, where all the angles between the members are all preserved. So we gave the artist this tool, so he was able to do that. Say, this is too dense, this is too light, I'm happy with this. So again, it's the use of digital technology to communicate is super key. And then just to continue this project, another thing that we did was, I mean, this is a pretty classic thing in the digital design world, is to move the supports around until we find the best configuration of supports that give maybe the least stress in the structure or the least deflection in the structure. We're also able to move the global shape of the structure such that we can control the deflection. So here we are looking at different configurations of form, subtle changes in form, just to reduce the deflection. And if you compare the original, and I think the original is maybe a little bit fuzzy for some of you, the black mesh, with the final one, which is the pink mesh, they're pretty similar, and it still obeys and still looks like a whale, but the deflection was 4 times better. Now, 4 times better doesn't necessarily translate into 4 times less material, but it's a hell of a lot less material, and it just works a hell of a lot better. So, again, use of digital techniques, good stuff. How do you build it? It's a very complicated thing to build. You've got all these tubes which are all possibly double curved, which is very, very expensive to fabricate. We've developed a series of techniques to decompose double curved tubes into lines of single radius arc, which then plugged together are a very, very precise approximation of the original tube. And single radius arcs are much, much cheaper to fabricate. So that saved a lot of money from the project. Talking about the workflow again, because again, the clock was ticking on this. We had to get it done before the winter storms set in Dundee. Every joint was calculated separately. There's a workflow set up where every single, the forces from every single connection were exported to a finite element package and a joint design package automatically, so we could check all of them. And that was a huge time saver. The thing was fabricated in the South Coast because they are the best fabricators in the country. The site was in Dundee, so what they did, they put it on a barge and they took it all the way to Dundee, where they built it. The artist had an exclusive deal with the Daily Mail to film it as it went around the coast. It was built. It looks great. Yeah, it's a great project. Lots of really nice local press, as well as the Daily Mail. And I talked about this before, about things being too complicated to build. Like, my God, how on earth are we going to build this? We'll never pull this off. So, what guerrilla tactics do we need to confront that fear? Well, I mean, some of them, and this is a project. I mean, at least one of these is a project I mentioned before. Can be easily tackled. Complex shapes can be easily tackled with geometrical techniques which decompose a surface into simple straight lines. So top left is the covering of a wagon which we're working on at the American Museum in Bath. It's a complex form, but it's straight lines of timber arranged on a double curved surface. Straight lines of timber are super cheap. top right, similar technique. This is the thing at Western Burt. We talked about the structure bottom left. That was also straight lines of 6 mil ply, a bend to the range to form a double curved surface. And bottom right, the pavilion called Steampunk, which I think I'll talk about in more detail in a minute, which is essentially the centerpiece for the Tallinn Festival of Biennale, architectural Biennale, a couple of years ago. So all very complex forms. How on earth do we pull this off? And also I talked about, social building and enabling what is outwardly a complex structure to be built by people who are not professional contractors. So this was the Burning Man Festival of 2018, the Central Temple. These are all volunteers. They were volunteers. They were architecture students. They were employees of Google. They were employees of Boeing. Brought together, and the only reason they could build this outwardly quite complicated structure is by some quite hopefully smart ideas about how you can decompose it into simple pieces. And again, I'll talk about that later as well. Number of timber shells we've done on the same lines. This is in Norway. It's a kayak cabin from very thin sheets of CLT built by architecture students. We're working with a very enlightened client here in the southwest of England who's got a huge master plan for a site. He's obsessed by concrete shells, which is fantastic for an engineer. So this is a prototype small shell. So we're using glass textile reinforcement, but we're able, again, by the use of scripting and sort of geometry manipulation to subdivide the surface into simple cutting patterns of glass textile reinforcement. He himself can literally cut with a piece of scissors and put them on, in this case, a clay mold for the shell. And there's the cutting pattern. And this leads to another project on his site, which is an even bigger concrete shell, which I just said the small shell is in construction at the moment. And it's a prototype for this bigger shell, which will also use glass textile reinforcement. And this hopefully would be done this summer. And apologies. Some of the other ideas flowing from this is modeling the reinforcement in this shell, and there's a whole separate presentation I could give on the research and the technology behind how we align the reinforcement. But modeling the reinforcement and using augmented reality maybe to place the reinforcement, that's one of the suggestions. And so we're talking of augmented reality. This is virtual reality. So we've used virtual reality a number of times. Not really that successfully, truth be known. It's great. It's a little bit faddy. It's a little bit sort of, well, my kids have got one, for example, and they love playing computer games on it. Whether it's how applicable it is to the real world, the jury's out. But what is very applicable is what I showed you before in the Goodwood structure. It's augmented reality. And this is one of our footbridges. And what we're able to do is literally go to site with an iPad or a computer, or maybe the Microsoft HoloLens set, which goes over your head. And you can see the real world as a background. You can see your structure in the real world. In this case, we're able to cycle through different variations of the parapet, show the client, say to the client, well, this is how it looks. And you get absolute instant buy-in from the client who says, I can see it now. That's really cool. So we've used that a number of times on footbridges, and we've used it a number of times on structures. I'll come back to an example of that in a minute. But one good example of a lot of the, I suppose, the philosophy of reducing complexity to make it simple to build was a number of timber cabins that we built in Hammerfest. Well, Hammerfest is the most northerly city in the world, apparently. It's in the Arctic Circle in northern Norway. Now, one site is on top of this mountain, and the other is a second cabin, which is on the opposing mountain peak. There's one computer model, there's one script. So we were able to take the architect's original vision of a curvy shell, an egg-like structure. We changed the form quite a lot, actually, to make it a more structurally efficient form. We broke down the surface into simple, flat panels of timber, simple, flat panels that somebody who doesn't have a huge crane or huge equipment can bring up to site on their back, literally, We set up all the screws as well within the same model, so that one person knew exactly where they should be screwing this together, and all the analysis within the same model as well. These are the people that built it. So this is literally the local community, all fueled by cake and enthusiasm. They're getting a briefing before they got going. It was taken to site in relatively low-tech gear. It's an amazing site. I've been there. So some of these photographs I might. It's just an incredibly desolate place. And there are the locals. You know, they're literally building it with their bare hands. The first cabin took, I think, 4 days to build. The second cabin took 2 days. And again, it was just by, I suppose, clever planning of the joints, hopefully clever planning of the elements so they were small enough and light enough to cart around easily, meant that these people who are not carpenters, who are not experienced contractors, can build something of value for the community themselves. That's a view from the finished structure, looking out at Hammerfest. Being Scandinavian, it's not just any old pavilion. It has underfloor heating, it has a wood-burning stove, it has designer furniture. It's a very cool place. So if you're ever in Hammerfest, I recommend hiking up the mountain to hang out for a few hours. And there's a nice sunset shot. And I think, again, another project which exemplifies some of these techniques, or captures several of these techniques of reducing complexity, but also addressing how we can build something that is outwardly very, very complicated, was this, which is a pavilion for the architectural Biennale in Tallinn, Estonia. It was won by a number of architecture students from the Bartlett in collaboration with the Australian Augmented Reality people I spoke about before. And I think the story goes, I think what I've heard is the academics from the Bartlett didn't expect to win. I think they entered just as an exercise, and lo and behold, they won, and then were expected to deliver this quite mad shape that they created. So they got in touch, and we talked about how we could break this structure down to its essence and how we could build this. There was lots of hand sketching of ideas and the various challenges and how we could hold this thing up. So communication was key. We, between us, sharing a common 3D model on a common platform, again, we were able to reduce this down to 2 elements. One, the timber planks themselves. And it's important to know this pavilion is called Steampunk. I should have said that before. It's called Steampunk. The reason it's called Steampunk is all the timbers are steam bent. So it's a series of very simple but steam bent timbers and a series of relatively complicated folded steel brackets which hold the thing together. How do you build such a thing in the wild? No, again, augmented reality. This is the Microsoft HoloLens. So you see the world through this. I mentioned this before. You're able to see, and these are the hologram guys and the architects. So you can see in the real world where you have to bend a piece of timber in its steam bag, and then you could match it to that. And they did the same thing with the steel brackets as well. You can see them. There's a man at his workbench, and you can see in the real world where he should be bending it to, and he bends it to. And you can get a pretty good accuracy, actually. I think inside, with HoloLens 1, it was something like plus minus 10 millimeters. With HoloLens 2, which is a new one, I think it's plus minus 3. So it's becoming a really viable working tool, actually. And they used it on site to build it as well. One of the hologram guys, Gwyl, he's Mr. building it. And that's what it looked like. Again, it's just a testament to tools, original thinking, and just sort of like a can-do attitude. So another adversary, and there aren't many more to go, so apologies. Another adversary is too little time. Now, I mentioned too little time before, and I think most of our projects probably have too little time, to be honest. The Goodwood project I talked about before, that was an amazingly quick time scale. But so we talked about it then, and how we can use various techniques to help us do things quicker. But another example of too little time was the London Design Festival Pavilion at the Victoria and Albert Museum last year. Architects Nebbia Works, who are all ex-Thomas Heatherwick, won the competition to design this very, very elegant, very refined, very sharp, literally sharp aluminium pavilion. Again, a whole bunch of hand sketching to sort of isolate the problems and come up with the various solutions to this. Lots of computation to rearrange the structure automatically to get it to perform better. So here we're moving the legs around and the cuts. So each of these legs, I should say, is formed by being a cutout from the sheet of aluminium and then bent into place. It's a very simple concept, but quite an elegant one. So we simulated that, but we also simulated the bending stress of the legs itself. So I think that was an important thing to do. That was the final model. That's what that was the intent. So very nice clamp details at the top. And we were, I think, all very pleased with the little bottom feet as well. So very elegant little feet on a literal sort of single pin at the bottom. And I mean, one thing I mentioned here is embodied energy. And now, I mean, most of our structures now, in fact, from now, I think all of them, we compare different options using the data set from the iStruct-T, well done iStruct-T, within our own Grasshopper plugins to look at different concept designs and the impact upon the embodied energy of the different decisions at the concept design stage. We now do that every project if we can. And this was a particular example of that, because aluminium is traditionally pretty bad, but this is a very new product. It's an aluminium product. They use I think it's a different smelting process to produce an aluminium with a far, far, far lower embodied carbon. So this is a sort of exemplar demonstration project for that. And you can see bottom left how it compared to standard aluminium, something like a third of the embodied carbon, I think. Fabrication started. There's some really nice details, stress relieving, corner teardrops. It's a combination of digital technology and craft. So it was built by men with a blowtorch and a bending machine, which is quite a nice, so it's a combination of the digital and the hand. And it was built on time. There it is in its context in the pool of the Biennale. The detailing reflected exactly what we hoped it would. So that was a great outcome for what was an incredibly fast-paced project. And I think the last project, I've shown this quite a lot, and I'm tempted to take it off presentations actually, but everyone likes this. In terms of timescales and how on earth do we deal with this? This is the central temple for Burning Man 2018. So architect Arthur Mamumani, who's a French architect who lives in London, he won, having been to Burning Man and built structures over a number of years, which we were also responsible for. He was awarded the Central Temple, which is one of the major elements of the Burning Man Festival. And his idea was, his vision was for this 50-meter clear span timber structure, which would be a spiritual space, which would be this space that you go and you'd leave messages for loved ones, and whatever people do at the Burning Man Festival, which I'm not allowed to go to. It's another story. And again, it's about decomposing this into simple pieces and understanding what the geometry does to the structure. And the big move here in terms of simplification was to say, well, rather than go for the traditional triangulated timber structure with a complicated steel node, is there any way we can actually prefabricate triangles, simple triangles, that they can have cut and made in a machine shop in the nearest city, which is Reno, brought to site, and then assembled by volunteers into the final structure. So that's the That was the aim. We did a whole bunch of work of engineering optimization, automatic optimization, reducing every member to the smaller size, blah blah blah. But what we found was actually that was counterproductive, because what it meant was there was a parts list that was so complicated, it was almost impossible to do on site. So we ended up just going for 2 sizes, arranged as efficiently as possible: a small piece, a 2x4 inch piece, and a 4x4 inch piece. Work started, the triangles arrived on site. They were assembled into modules. The modules were assembled into what's called banana trusses. And the banana trusses were then arranged around the central hub. And this is all volunteers. In this instance, they did have access to some plant. Again, these are people who, as I said, were architecture students. They're employees of Google, Boeing, and various other people. And that was it. It was built. And it was an amazing space. This is the spiritual aspect to it. People were really engaging with that. That's the drone shot. Again, the obligatory drone shot. And then the joke is, and what we always like saying, it took us 9 months to design it. It took 2 months to build, maybe. It was up for 5 days, and then they burnt it. So slightly disheartening, but quite good fun in the sense of where we've made structural decisions as to which parts of the elements needed to be reinforced, etc. They were some of the elements were burnt first, and you could see the whole structure collapsing just how we predicted. So it was the ultimate real-world test of the structure. And that's it for me. Thank you very much.
Thank you, Stephen. That was everything I was hoping it would be. Absolutely fascinating to see some of the insight and thoughts that you put into, and your team put into your projects over there. Right, we've got some questions coming in. I might just start with one from me, as I see we're just lining up some other ones. But I suppose there's lots of technology here, and do you see applications of? I mean, they always say like Formula One informs other kinds of motor engineering, for example. But do you see kind of how we can practically use some of this knowledge to sort of make our structures more efficient and perform better? And
sure.
Could sort of the engineering optimization inform more architectural design to be more of a form generator for architects to play with?
Yeah, absolutely. And I think that you only have sort of limited time in these talks, and I think there's so much you can sort of leave out. And I kind of regret leaving some of that out, to be honest. But a couple of examples. We are working on a waste to energy plant in Swindon. The same client who's kind enough to commission us to do those concrete shells. An outlet, it's a very simple rectilinear form. So the original presumption was it's a steel frame portal shed. But we said, look, give us a chance here. We'll try and use, I suppose, the creativity and the tools we have to really refine the structure. We can make a timber structure. So we can make a timber equivalent to your portal frame shed that's no extra cost. That was the ambition. So we did. So we used, in this case, Karamba and Grasshopper, all those tools to rearrange structures, all elements automatically until we had a configuration that was actually as cheap as the portal frame shed. So the client was quite happy to do that. And for another talk, I'll put that up. It's a very simple structure outwardly, but it's refined to its ninth degree.
That's fantastic. Yeah,
and also, so I mentioned another one, which I also regret not putting in, about social building. We're working with one residential house developer here. So it's his own house, I should say. So he's building his own house in the outskirts of Bath. But we've got a reciprocal timber roof, a 4-way reciprocal timber roof. It's all made from CNC ply, but he's going to build himself. So what we've done is, again, produce for him. Well, we've done the 3D model. We've produced for him all the cutting files, so he's able to procure his own materials and build his own structure. So again, it's a house. It has a reciprocal timber roof, but it's from a private client, and he doesn't have to commission a masonry, or he doesn't have to commission a contractor who quite often says, "I don't understand this." So there are. I mean, we're very passionate that there are very everyday applications to this.
Yeah,
So
I always thought. Yeah, I always thought if you can draw it and draw every single part, and you can effectively build it yourself, then you're sort of getting somewhere towards making other people buy into it.
Absolutely, and this is a lot of the work that you've done, I know. So I think we're both of the sort of similar mindset on that.
Yeah. A few questions about analysis. What FE package are you using, and the joint designs which you automated? I guess you've got some sort of scripts and API stuff going on.
Yeah, so analysis packages are several. So if you took one workflow, it could be, we'll take Goodwood, for example. It's all form found and initially analyzed with our own K2E software. And then it was squirted two ways. One to the Karamba finite element analysis within that you can plug into Grasshopper. And secondly, we've got an automatic link to Oasis GSA, which is our normal analysis package. Mm-hmm. So it's a great way of A, cross-checking what you've done, and B, there's always going to be different functionalities and different packages. GSA is very good at dynamics, for example. Karamba is very good at initial member sizing. So, and it's the best way of cross-checking. So we use several different finite element packages. We use a solid body FE package called Mechway. We use Idea Statica for the joints. We've got workflows which connect them all together. So yeah, it's a number of tools really.
Yeah, that sounds very similar to what we do. So
yeah.
You mentioned OpenFOAM. Have you found any other open source computational tools to be useful?
One of my more slightly nerdy colleagues might be better placed to answer that. Do we? How many more open source tools do we use, nerdy colleague? Apart from OpenFOAM.
A bunch of model conversion tools, like CAD conversion tools. We've got some good stuff on that. Section properties tools.
Okay, there's a bunch of section properties tools, CAD conversion tools. So yeah, we use a number of things. And also lots of plugins to Grasshopper, obviously.
Yeah. No, they're all. I mean, as you say, they're tools, and making them all work together is part of the fun, I guess.
Well, yeah, absolutely.
Someone's curious about how you work out the stresses in the elements. I think using those tools is probably the answer to that one. Presume you're involved in analysing the structures in the temporary case. Saw people standing on the incomplete timber shell structures. Does this take much more time in comparison to designing the final situation, or is it simply a case of inputting the structure to the relevant stage in your computational model?
Does it take more time? I suppose it depends on the particular structure. If you took the Goodwood, as an example, I would say the analysis of the temporary case was very critical, and we did a lot of work on that, because even to the point where the bits of it were held up by a crane in midair, and then bits had to be joined to another bit, and how much was stable, how much do you need to build before it was stable, and that was a big part of what we did. How much work it was, once you set these scripts and these 3D models up, it's actually relatively simple to take elements of them, I think, and then to analyze them. So that's one of the beauties of doing it this way. It's certainly something we take very seriously.
Yeah, so there's another question about buildability and CDM compliance, but I guess that kind of analysis is key to kind of understanding if something is just going to buckle over.
Yeah, I mean, I get this question quite a lot. I mean, don't forget, we are structural engineers, so we are checking it with different package. We're taking the output of the different package, and we're doing simple hand checks against the package. We're not just leaping in something and trusting the results. We're taking a very critical engineer's eye over what we see, or we might build the model up into small bits first to understand that before you plug it all together. So you still got to be an engineer. These are all tools which enable you to design better stuff quicker, but you're still an engineer.
Exactly. Hi there. Thanks for sharing. Given that technological tools are extremely useful in addressing a lot of the problems, why are hand-drawn diagrams still important? Do you have an example where this is important on a project? I mean that's early stage stuff, isn't it? And
Yeah.
Kind of just getting. I mean, you've got to have the right idea to analyze, haven't you? That's what.
Absolutely, or you the right number of, or a good bunch of ideas. And I think that it's maybe because I'm slightly old school and I like sketching.
Yeah.
I like forcing people to sketch things, but it's all about A, communicating, and B, taking. I'm a firm believer. If you don't, how can you understand the thought process? So you understand the thought process by drawing things out. For me, anyway. And so, the act of drawing or the act of sketching is a way of drawing these ideas out. Yeah, I personally find, and we often find if you draw things by hand, what comes out the other end could be the really complicated solutions. Oh, let's use a Nervy-esque principal stress line approach for this structure here. Oh, I've sketched that. Well, that's one of the options. So I think it absolutely fits in with what we're doing. And I said I'm really, really passionate that we don't come across as a bunch of nerdy computer users. We're not. We're engineers. We're sketching ideas. We're producing things. We're doing complex things with some of the tools we have.
I often think that for using parametric design, you need to know what your parameters are.
Right. Yeah. Absolutely.
And that normally comes from
absolutely, or what the right parameters are.
Yes. Yeah. Exactly. Do you have any recommendations for further reading on things like form finding techniques, etc.? There's a whole bunch of books, I'm sure that.
God, there's a whole bunch of books on my shelf behind me. I suppose you probably can't be immersing yourself into some of the classic approaches, Fry Otto, Nervy, things like that. So I mean you'd be surprised how much of the stuff that was done, Gaudi obviously, how much of the stuff that was done many in Mannheim Shell, all this is still relevant. A lot of it still comes back. So I think grounding in the classics is probably a good thing.
Yeah. It seems like the guerrilla tactics required for projects can be very novel. Is it challenging justifying the legitimacy of your guerrilla tactics?
Yes, sometimes, but I'd like to think we do enough cross checks, enough simplified analysis, and very clear engineering reports that we hand over to someone who can then understand what we're doing. Again, I reiterate the fact that we're still engineers. We still have a duty to, look through what we're doing, check what we're doing, and communicate clearly what we've done.
Yeah, I mean, there's a question here about fatigue and long-term use, and that all falls into that as well, doesn't it? The sort of engineering design is,
I think,
the core thing about it.
Fatigue is the bane of our lives, to be honest.
Completely a nightmare, yeah.
Yeah. So no, it's taken very, very seriously.
Well, yeah, if you want to make a structure fall down, fatigue is a good way to do it. Well, that's been great. I mean, it's come up just past 7, so I think we might try and draw it to a close and just say thank you very much for a super evening. Really, really great to see the models on the shelf behind you as well in your studio. It's like a true design studio, and the fact that you're building things. I mean, all these things are fine, and you can have as many simulations and ideas and competitions, but the real skill and pleasure in life is building stuff, and it's great to see so much stuff that's that you're designing is getting built, and we're not looking at a presentation full of competition ideas. So it's really refreshing, and I really enjoyed sort of seeing how you've got into the loads of different parameters and thought processes and fabrication processes, and allowing them to inform the design of stuff. So it's thank you again for sharing that, and I look forward to hearing about the shed in Swindon.
No problem at all. Oh yeah, look out for the shed. Look out for the big concrete shells. They'd probably be first, actually.
Yeah, good. Keep putting them on the website so we can see what you're up to.
Will do. Brilliant. All right.
Right.
Thank you, everybody.
I think that brings it to a close.
All right. Okay. It's good night from me then. Thank you very much.
It's good night from him. Good night from me.
Bye all.